What is the wavelength?
The distance from one crest to another crest.
The distance between the two trough and distance between the
Yes.
crest, right? Two crest
Yes.
or two. Is known as the wavelength. Okay, and what was the relationship between the wavelength and the speed?
It's equal
C
to the
u lambda,
product
right?
of, yes.
And we also discussed that and frequencies. What is the definition for frequency?
Um, like waves per second.
How many waves are being generated in 1 second? Okay.
Yes.
So how many waves are being generated in a second? That is known as frequency. Okay. And C equal to nu lambda. What is wave number?
The number of waves.
Or unit length. Okay. What part of the electromagnetic spectrum can we see with our naked eyes? What part we can see with the naked eyes?
Visible.
Hmm?
The visible wavelength.
Yeah, visible region. That is known as the visible region of spectrum. Got it? And that is the
Yes.
colors are vibrio, okay, violet, indigo, blue, and the red one is having the longest wavelength. That's what we discussed. So red lights are used in signals because they can travel far apart. Got it? That's what
Yes.
we had discussed. So this is the and this is basically yeah, the uh, the wave nature of electromagnetic radiation. Is it clear? That tells us
Yes.
that the electromagnetic radiations are waves, but waves of what kind? They are the waves of electric field and the magnetic field, which are moving perpendicular to each other and perpendicular to the direction in which they are moving. Right. Next is
Yes.
there are so if a light is coming towards me, it is the waves, okay, which are coming to my face, okay. So that is the electromagnetic waves theory of spectrum. There are many experiments which can be explained by the electromagnetic theory. Got it? And
Yes.
that is diffraction and interference. Diffraction and interference. Are the evidence of wave nature of light. Because if we are assuming that wave nature, okay, we need to know some experiment which can prove that the light is having the wave nature. And what are those experiments? Those experiments are basically the diffraction and interference. So diffraction and interference explain the wave nature of light. What do you mean by diffraction?
Moving, bending away
Pardon?
from surface. Diffraction is bending.
Yeah, bending of light rays around an obstacle. So suppose if a ray of light is coming in the room or in a closed room which doesn't have any windows, we see that the ray of light is coming straight, and we also have the light spreading in the whole rest of the part of the room also. That is diffraction. Okay. So if even if a single ray of light is getting into the room, you can see the whole room is lit up. Not completely, but the other areas where the light ray is not reaching, that also receives light. It is because of the diffraction. Okay, some light is bending around the corners of the edges of the windows and doors through which the light is coming. Okay, and what is interference?
Um, um, in between something.
Yeah, interference is actually
The,
when you, yeah, when you take two light source, you do the experiment also. Then monochromatic light source of same wavelength, right? Just one wavelength, and at some places the light rays are coming. Okay. Suppose I take a sheet, and this I put two holes in that sheet, and light rays coming. So you see that these are the waves of the light which are spreading. Right? Just like the water waves, when you drop some stone, you have a circular waves. So at some point, you will find that the two waves, light waves are meeting together. Got it? Can you see these points?
yes, sir.
So you can see these points. So these are the points where the rays get added up. Okay. And when the rays get added up, these points brighten up more. Is it clear? So when the
Yes,
two
sir.
light waves combine together, okay, so the light waves there are certain particular conditions where we can see the diffraction. Not everywhere is it possible to see. Okay. And so basically, when the two light rays combine together, so that there are some point where the waves that both the crest meet. So that are the point where you have more intensity of the light. There you find the light more brighter, and there is a point where the crest and trough meet. Crest is the and trough is the lower portion. If they meet, the wave cancels. So diffraction is basic. This interference is basically addition and subtraction of waves. Okay, means addition, meeting of wave. The two wave meet. They can meet either from the crest, or they can meet either from the trough. Okay, and the wave can get added up or they can get cancelled. Addition and cancellation. Of waves is known as diffraction. It is like suppose if there are two waves meeting like this with the two crests, so you will have final wave, more giant wave being formed. This is addition happening. Got it? And suppose if you have a crest
Yes.
and you have a trough meeting, right? The wave will, it may become, its amplitude will be lower. Cancellation happens. The energy, cancellation of energy. So addition and cancellation or addition and subtraction of waves is known as diffraction.
Okay, sir.
So what are the two experiments which, so these happens with other waves also. And how we see the light rays are being added up, we see a more brighter spots that tell us that the intensity is increased. The two waves have met together. And we see some dark spots also in this region. There are certain regions where you have the dark spots. So those are the spots where the light waves get cancelled, one crest and one trough. So this diffraction is basically addition, not diffraction. This interference is basically the addition and subtraction of waves, and that tells us that the electromagnetic waves or the light waves undergo interference. So it is light waves are electromagnetic waves. Okay. Diffraction and interference, both are the evidences of wave nature of light, because these properties are shown by wave. Is it clear, Nabila?
Yes, sir.
Now you have, there is one more theory. So some of the experiments like diffraction, bending of light rays, and addition of light waves and cancellation of light waves when the two light waves meet, that is interference, that proves that the light is wave. But there are certain experiments which help us to prove that the light is not wave, the light is particle. So dual nature of light. As you were talking about, we discussed the wave nature. And so C equal to mu lambda, this already we discussed. Yes.
Yes, sir.
And now we need to discuss the particle nature of that. So what do you mean by particle nature of light? Yeah, Maha, good evening.
Good evening, sir.
So we were discussing the nature of light, dual nature of light. Light can be wave and light can be stream of particles. What these particles are known as? These particles of light are known as, it's a very common.
Proton fusion.
Yeah, exactly. photon theory. So if a light is coming towards me, wave nature will tell us that it is a wave, electromagnetic wave of electric and magnetic field approaching me. It is an electromagnetic wave. And if it is particle nature, it is going to tell us that light is a stream of particles. If a light is coming towards me, it is a stream of particles continuously coming towards me, and that stream of particles is known as photons. So what are the evidences of particle nature of light? What are the evidences of wave nature of light?
Shadows.
Evidence, shadows. Yeah, but we need to be more scientific. So how a wave can make shadow? Okay. Just now I told just a few minutes back, evidences are diffraction and interference. You will have a whole chapter on diffraction and interference in class 12, right? In physics. So don't worry about that. Okay. Diffraction is bending of light rays around the corners, sharp corners. And interference is when the two light waves meet, they can get added or cancelled. Okay. There are certain experiments which can be justified by taking light as stream of particles. Is it clear? So what are the
Yes.
evidences, experiments which can be explained by the wave nature, the particle nature of light? So evidences of particle nature. And they are black body radiation, photoelectric effect, line spectra of an atom. So these are the phenomena which can be explained by assuming that a light is not wave, but it is a continuous stream of particles, and those particles are known as what these
Photons.
particles are photons. Is it clear? So black body radiations, photoelectric effect, variation of heat capacities of solid at higher temperature. Normally we take the heat capacity as constant, okay, and the line spectrum of an atom. Okay, these are basically the evidences of particle nature of light or the photon theory of light. Is it clear?
Yes.
So what do you mean by uh, uh, quantum nature? This is also known as quantum nature of light or the particle nature of electromagnetic radiation. So I'm going to write the points, and we have some of the experiments in chemistry, photoelectric effect, we have a line spectrum of atom, we have in detail. Okay. So that we are going to discuss in detail. Okay. So first we are going to discuss the particle nature of electromagnetic radiation. It is also known as quantum nature of light. Quantum theory, or Planck's quantum theory. It was given by Max Planck. Or photon theory. So first we will try to figure out what this theory is, and then we will try to understand the experiment. So wave theory tells us that light is being continuously received in the form of waves. The waves are continuously coming towards us. Just like when we are sitting on a seashore, we can see the continuous waves of water approaching us at the shore. Okay. But if we talk about the particle nature of light or the Planck's constant theory, as per this theory, the light is not emitted or absorbed continuously in the form of waves, but rather it is absorbed or emitted by a source discontinuously in the form of packets of energy. Is it clear?
Yes, ma'am.
Light, or I'm going to write the point, light or radiation, it is one and the same thing. Light is the visible part of the electromagnetic waves. Okay, visible, which is visible to us, light or radiation. It's not emitted or absorbed continuously, but rather discontinuously. So light is released or absorbed. If a light is coming towards me, actually small packets of energy are hitting my face. So it is not continuously received or released by a source. It is it is rather discontinuous. But we don't see light discontinuous. It is my face is continuously being lit up by the light. It is because the particles are very large in number. Okay, they are very small particles of energy which are approaching my face, and they are very large in number and very fast they are traveling. So it appears that they are continuous. Okay, but as per this theory, light is not continuously received or released. It is received or released discontinuously in the form of small discrete packets of energy called quantum or photon. If I talk about the visible light, but rather discontinuously in the form of small discrete packets of energy called quantum of photons. Right? So if I'm having suppose surface, so continuously you can assume that this surface is receiving these small packets of energy. These packets are actually lighting up the surface. Is it clear? Now let's
Yeah.
talk more detail. This is just a qualitative part, not the quantitative, because it is talking only about the particles. There is nothing numerical being mentioned. Okay, so we can't in science we can't rely only on the qualitative part. We need to write all the details and the formulas. So the second point is the energy of each photon or the particle of light, which you can call as quantum, is directly proportional to its frequency. Directly proportional to the frequency of radiation. So I am receiving light. The energy of a photon, E, right? It is directly proportional to the frequency of the radiation. What do you mean by frequency? It is represented by Greek letter nu. So what do you mean by frequency? Frequency is how
Pattern.
many, yeah, how many vibrations per second we are receiving. Right, ma'am? Nabila?
Yeah.
So it is,
Yes.
what is the unit of frequency? Per second or hertz, HZ. Got it?
Yeah.
the units of frequency per second. So how many vibrations we are having per second. So frequency is not only for the light, but it is also for other objects also. Like in the school lab, you are going to perform some sound experiment with a tuning fork. Okay, for sound waves also, you can talk about the frequency. Okay, is it clear? You might have
Yeah.
studied in your
Yes.
ninth class. Like the females have a higher frequency voice and the males have lower frequency voice, right? It is more thinner voice means higher frequency, right? So similarly, the energy of a photon or a particle of light is proportional to the frequency of the radiation and is independent of its intensity. So that particle energy of the particle is directly proportional to the frequency, and because I need to energy of a photon is directly proportional to the frequency, and because I need to remove this proportionality sign, I need to put a equals to sign. So I need to put some constant. Is it clear? And that constant is h. So this is the energy of a single photon for a particle of that. What is this h? So suppose if I'm receiving the light on my face, imagine that lot of photons are striking my face. That's But it is not continuous, it is discontinuous, but you can see the light on my face continuously. It is because a lot of particles are coming. They're very fast, so that's why you see the light coming continuously. But actually, if you get into the particle nature, it is not continuous. It is small particles which are of energy, which are hitting my face, okay, or a surface. So the energy of each particle is h into its frequency. H is the known as Planck's constant. Its value is, do remember its value, very important. This is just a universal constant. Now you are going to use it in physics class 12th also at many places, and in chemistry 6.626 into 10 to the power minus 34 joule second. Is it clear?
Yes, sir.
Yes, sir.
So energy of a single photon is going to be, if the frequency of the light is not given, you can put C by lambda. Got it? Is it clear?
Yeah.
So next is, so this is the energy, this is the photon. Now we are, so in Planck's constant, okay. I hope you understood. This is a very small amount of energy, 10 to the power minus 34 joule, because that particle of light is very small, okay, and that energy has to be very small. So whatever the light which I'm receiving, whatever the energy which I'm receiving, that cannot be given or taken continuously, but it is can be given or taken discontinuously in the form of packets of energy. Okay. So the total energy received or released will be n times, will be the whole number multiple of the energy of a single photon. Is it clear? So total energy which is released
Yes, sir.
will be n times. Suppose I can give 10 photon, 20 photon. Is it clear?
Yes, sir.
Amount of energy. So total energy is not continuous. It appears continuous, but at a microscopic level, not even microscope, much smaller than that, it is not continuous. It is basically n times h, or it is n into h. Well, got it? Is it clear? It is in the
Yeah.
integral order. Suppose I can get 10 photon, 20 photon, 30 photon, like that, right? So total amount of energy released or absorbed by any source is the whole number multiple of the energy of a single photon. The next point is all these photons or each photon travel with the speed of light because they are particle of light. So they should travel with the speed of light. Okay. So each photon, this is quite obvious point. Because photons are particle of light, so they should, we expect them to travel with the speed of light, and that is c. That c is 3 into 10 to the power 8 meter per second. Is that clear or not?
Yeah.
So let's do some questions. So this is, so suppose if I'm, it is just like quantum nature of light. Suppose if I'm standing on a ramp, slope, right? Or if I am moving up through stairs, right? So I can stop anywhere I want. I can move up, I can move down, I can stop anywhere. My energy is can change continuously. Okay, is it clear? I can move little bit up or 1 centimeter down or any. I can move up and down and stop at any position on this slope ramp, right? I hope this is clear. So my energy, my potential energy, MGS, that can have any value. Okay. But suppose if I am going up through stairs, so I can come here or I can come here, right? Or I can stop here. So my energy is not changing continuously, it is changing in terms of the height of the steps. Are you getting my point or not? It is like quantum nature. This is known as quantum. What's like what is the smallest currency you are having in UAE? Dirham, and earlier you were having fils, right? I think.
Yes, sir.
Yeah, fils. Now do they have fils?
Yes, sir.
Okay, they have fils. Okay. So in India we have paisa, and paisa now it is stopped completely because that is too small, right? And rupee is the unit. Okay. So I can pay someone in term of 1 rupee, 2 rupee. I can't pay 1.5 rupees to someone because the smallest coin is 1 rupee or 1 rupee as of now. But earlier in my childhood days, we were having 50 paisa, that was half of a rupee. Okay, 25 paisa, that was 1/4 of a rupee, right? So earlier times I used to pay 1.25 rupees. Okay, or 1.1 rupees. Now I can pay just 1 rupee, 2 rupee, 3 rupee, okay, in multiples of one. So I want to explain this quantum nature because the energy is being released and absorbed in the form of photons or the packets. So the energy which is released or absorbed can be the integral multiple of the energy of a single packet. You can't have energy of photon like this. Can we have energy, receive energy from light like this? No. Can we have energy of 1.5 photons? No. Can we have energy of 2 photons? Yes. So those complete energy packets of energy can be either received or released by any atom or any source of light. Okay. That is the quantum nature of light. Got it? Quantum means it is changing in steps, in integral whole number multiple of that energy of one particle. Okay. So I hope this is clear to everyone. Any doubts on this? Maha, Nabila, any doubts?
No doubt.
Okay. So let me give you one question. Find the energy and through this question, let me tell you a shortcut also of uh, of a single photon, just one single photon, which see with we can't see these particles of light. These are all experimental values. Okay. Find the energy of a single photon of violet light. Having wavelength of 400 nanometers. So violet light is coming towards me, and its wavelength is 400 nanometer. So basically, this is coming in the form of packet. If I assume it to be coming in the form of small packet, continuous stream of packet, what is the energy of that one single packet of violet light? Or one single photon of that violet light? What is the energy? So you are going to apply the formula. What formula you are going to apply? Then?
C equal to
Yeah, the energy of a single photon Got it? Is equal to Planck's constant times its frequency, or Planck's constant h c by lambda. Okay, is it clear? First, what formula you need to apply, that you have to tell me. Okay, so this is as per the particle nature of that. Okay, is that clear?
Yeah.
So I need to put the values. What value do I need to put in place of h, in place of c, in place of lambda? What values do I have to put? H is 6.626 into 10 to the power minus 34 joule
So
second.
can't we just take it as 7 or something?
Pardon, can't we just take?
H as 7 because it's gonna take a long time to.
Yeah, it is going to take long time, but or you can take it as 6.6. Okay, not 7, right? Uh, I will tell you one smaller trick also, right? And C is 3 into 10 to the power 8. Also keep track of the units, meter per second. This is the velocity, right? And second will get cancelled. And lambda is in meter. Lambda is in meter, right? So lambda is in meter. So I'm going to take how many meters? What do you mean by 400?
400
Nanometer.
only, right?
400 nanometer. This is nanometer. Nanometer is how much? Nanometer is 10 to the power minus 9 meters, right? Is it clear?
Yeah.
So this is going to be a very cumbersome task. Nano is 10 to the power minus 9 meters.
You can
To solve
remove the
the
meters, right?
hmm?
You can subtract the meters and
Yeah,
divide the meters.
meter will get cancelled and you will have energy final unit as joule, but that joule is going to be very small because you have 10 to the power minus 34 being there present in the numerator. Is it clear? It's a very small value,
Yeah.
and so obviously that is going to be very small because you are talking about the energy of a single photon. It is such a small particle that you can't even see it. Okay, you can't see, you can't just you need experiment tell us that it should be there. Okay, we can't see it by any means. So now what to do? Okay, so now I will tell you one important trick. H into c, the value of hc, because both are constant, instead of multiplying them again and again, 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. Okay, get them multiplied. Okay, and this hc is 1240. 1240 electron volt nanometer. Got it?
Mm. Yeah.
Electron volt nanometer. What is electron volt? Electron volt is also a unit of energy, but a very small unit of energy. It is equal to the charge of the electron 1.6 into 10 to the power minus 19. That was the charge. And that charge you can take it as joule. One electron is equal to the joule. In joules, it is equal to the charge of the electron in joules. That is the energy. That is very small, 10 to the power minus 19. But what is the what is the sense of taking the energy in electron volt? Because we are talking about very small amounts of energies. Okay, is it clear? So electron volt will now be a very small amount of energy of electrons and all. You are going to measure it in terms of electron volt. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. Got it? And HC is
Yeah.
HC is 124. HC, the combined unit of H and C is 1240 electron volt nanometer. This is a very good number, 1240. But the units you have to be careful. These are not in joules. Okay, will you remember it? Or either you have to struggle if you want to get into joules and meter per second. If you are going to, as per the standard units, you have to struggle with all these values. Okay, is it clear?
Yeah.
So now what to do? Now put this value, and so energy of a photon. I'm using this method. Okay, hc by lambda. Nabila, are you getting it?
Yes.
1240 electron volt. Electron volt is some new value of energy. It is the product of H and C in electron volt. Okay, so remember this value because this makes the life very easy. Divided by 400. Now the convenience is that you don't have to change the nanometer also, because in the numerator you have nanometer, you can put that the wavelength directly in terms of nanometer. Are you getting my point or not?
Yeah.
So nanometer will get cancelled. You will have the total energy as now this is very easy. 12.4 by 4, 4 3 is 12, 4 1 is 4, 3.1 electron. But it is somebody want in joules. Let's put the value of electron volt 1.6 into 10 to the power minus 19 joules. Multiply by 3.1, get it in joules. But in cases of electrons, in cases of atom, we have introduced a new unit, which is a very small unit. Okay, like in the previous chapter, we introduced the unit of mass U, right, or AMU, atomic mass unit, that was equal to 1.66 into 10 to the power minus 24 grams. Okay. Similarly, in this case, we have introduced a new unit of energy, that is 1 electron volt. What is the value of 1 electron volt in joules? It is equal to the charge of the electron 1.6 into 10 to the power minus 19. Got it? Is it clear?
Yes.
Use this 1240 electron volt nanometer, but if you are using it, put the wavelength in nanometer. Very important. Okay, don't put the wavelength in meters and all. That will go wrong, because in the numerator you have in nanometer, so denominator in the wavelength should also be in the nanometer. Got it? Is it clear? So this is the energy of a single photon of violet light. Very small energy, right? Let
Yeah.
me let me take another example. Suppose there is a bulb of 100 watt. It emits a light of wavelength 400 nanometer. It emits a light of monochromatic light. Monochromatic means of one single wavelength. Okay. Normal light wavelengths are not monochromatic. Suppose if I'm sitting in this light, white light, this is not monochromatic. It can have many wavelengths. Okay. Okay. Monochromatic single wavelength. Okay. 100-watt bulb of emits a light of wavelength 400 nanometer. Means it is a violet color bulb. Calculate the number of photons. So we have a 100-watt bulb. And assuming that all the energy is being converted to, that is not mentioned of course, but I'm telling from my side that all this energy is being converted to photons, energy of the photons. Got it? So you
Yes.
need to tell me how many photons are being released in 1 second by this bulb. So this bulb is continuously releasing the particles in all the directions.
So 100 volts will be the energy.
Pardon? Yeah, 100 watt. What is the unit of energy per second? It is the unit of power. It is actually joules per second. Got it?
Yeah.
So how we are going to do it? So this is the energy per unit time. Power. Power is what? Okay. So energy per unit time. Right? This you might have studied in your junior classes also, in 10th class also.
Yeah.
And you will be studying it again. Okay. So energy per unit time is power. And this is the power of the bulb, that is 100 watt. And E by T. Energy is the total number of photons emitted per second into energy of one photon by T. Is it clear?
Yes.
This
Yeah.
time is in second, right? So we can have n by t number of photons emitted per unit time. Got it? Are you getting my point or not? Because this question is
Yeah.
asking number of photons per unit time. Per second means per unit time. So what is the energy per unit time? Energy per second. Energy per second is what? Okay. So 100 watt. Got it?
Yes.
Equal to the number of photons per second into energy of photon. Now you have to be careful, very careful. 1240 electron volt nanometers. divided by lambda. Lambda is how much? 400
400.
nanometer. This nanometer is not going to cause any problem because it will get cancelled. But this electron volt is going to cause a lot of problem because the energy on that side is joules. So you need to convert this electron volt into 1.61 electron volt. EV is 1.6 into 10 to the power minus 19 joules. Got it? Is it clear? Electron volt also I have expressed in joules. Is that clear or not? I have not put
So
electron volt.
which,
Yeah. Or either you can use that 6.6263 into 10 to the power. You can use directly that joule value. But there you need to do some calculations. Or you can use this electron volt value and put the electron volt as 1.6 into 10 to the power minus 19 joules. Are you getting my point or not?
yeah,
So N by T is 100, and that was 3.1 from the last calculation. Got it? So this is basically 100 by 3.1 into 1.6 into 10 to the power 19 joules. Got it or not? So let's see how much we are getting. 100 divided by 3.1 into 1.6. We are getting 20.16. Got it?
mm,
So it is 2.016 into 10 to the power 20. Not, this is not joules. This is per second. Because joules will get cancelled. This is joule. This is 100 joule per second. What is joule per second? And this is these many joules. So this per second. These many particles per second are being released by the bulb. Are you getting a point or not?
yeah,
Yes, sir.
So this is basically the photon theory. Is it clear? So suppose as per the photon theory, very important point. Okay, so bulb, how many photons is, so bulb, that energy is in joule per second divided by the energy of one photon in joules. So that many photons per second are being released. Got it? So 100 watt divided by energy of one single photon. 100 watt per second it is releasing. Okay. 100 joules per second it is, 100 watt means 100 joules per second it is releasing. So divided by the energy of one photon in joules, right? That's what we did. So if you have 100 joules being emitted per second, divide by the energy of a single photon, you will get how many photons are being released. Okay, how many photons will make the total energy equal to 100? Is it clear? Got it?
yeah,
That's what we did in this question. The next very important point is that intensity doesn't change the energy of a photon. In the quantum nature of light or the particle nature of light, intensity of light is controlled by number of photons. What it means? It means that suppose if I'm having a dim light, yellow light, which is dim, and bright yellow light, what's the difference? If I'm having a faint yellow light or if I'm having a bright yellow light. Okay. Yeah, Navi, help.
This faint one is more better, like for the eyes.
And the faint one, as per the particle nature, it is because the light is yellow, let's say. So the faint light is having less number of photons incident per unit time. That faint light is,
Mm.
let's say, suppose, right? Let's say it is dim light, okay, or faint, not very bright light. So it is carrying dim or faint yellow light, right? So it is carrying the photons of yellow light. Okay. And let's say
Okay.
it is dim, faint, or less intense, low intensity. I should write low intensity. Let's say it is low intensity, dim, low intensity means dim or faint yellow light. Okay. And the next is bright yellow light with more intensity. Bright yellow light with higher intensity. So low light is having less number of photons. The energy of photons is same because it is yellow light. So the energy of the photon is same in both the cases, right? But
Yes,
why
yes.
one of the light is dim or low of low intensity while other light is very bright, has a very bright intensity?
Mm.
Energy of a single photon is same in both the cases as it is yellow light. Because it is yellow light, so the energy is same. this photon energy is equal to h nu. Of this photon is same energy equal to h nu. Energy of a photon is same, but that bright light is appearing bright because it is carrying more number of photons. That is more intense. That is higher intensity. Are you getting my point or not?
Mm.
It is higher intensity because it is carrying more number of photons per unit time, and the less bright light or the dim light or the low intensity light is less intense because it is having less number of photons. Is it clear? Right?
Yes.
So there is an experiment which tells us about the photon theory of light. Okay, what is that experiment? I have discussed four. I have written four phenomena which can be explained, which can't be explained by particle. There are some experiments which can be explained by photon theory. There are some experiments which can be explained by wave nature. Diffraction and interference can be explained by taking light as wave, and black body radiation, photoelectric effect, okay, and line spectrum of an atom. These are very important. These two. They can be explained by assuming light to be of the particle nature. If the light is of particle nature, we have these kind of things which we need to know. So let me talk about the photoelectric effect. What do you mean by photoelectric effect? Who studied photoelectric effect? Photoelectric effect was studied by Albert Einstein. Okay, and it is the proof of the particle nature of light. It is the proof of the particle nature of light. Particle nature of particle means what that particles are known as. It is the proof of photon. Particle nature of light or photon theory. So what this Albert Einstein studied this phenomena, photoelectric effect, and what it means. It means that suppose if you take a metal, okay, and when the metal surface is irradiated with light, okay, means it is being continuously hit by photons, stream of photons, okay. These photons are going to strike the electrons on the surface of the metals atom, okay. Electrons on the surface of the metal, or electrons, these photons are going to hit this is the atom, and these are the electrons. These photons are going to hit the electrons on the surface of the metal, and these electrons are being knocked out of the surface of the metal. Is it clear?
Yes, sir.
You will see the emission of electrons from the surface of the metal. So it is the emission of electron observed when the surface of a metal is irradiated by a light of certain minimum frequency known as threshold frequency or certain minimum energy, light of certain minimum energy. Known as work function. It is just like, so the photons are coming, they are hitting the metal surface and they are knocking out the electrons. Got it?
Yes, sir.
Electron will be knocked out only if the photons have certain minimum amount of energy. If it is just like, suppose I am hitting something and trying to move a table, okay, with my kick, will the table move or not when I try to hit it? It depends how hard I hit, right? If I hit it with a less
Yes.
energy, nothing will happen, the table will not move. Is that clear?
Yes.
I need to hit with certain minimum energy to move the table or any block or any book, okay, because to overcome the friction. So same is the case with the metals also. So when the metal surface is irradiated with a stream of light, okay, a photon, that photons strike the metal surface and they knock out the electrons. And this emission of electron is observed, and this is known as photoelectric effect. So this is emission of photocurrent. This is known as photocurrent. Got it? Photocurrent means it is the current
Yes.
or the flow of electron which is being released when the metal is put into light, but that not every light, it should have minimum frequency. It need to have some minimum frequency depending upon the nature of metal. What that minimum frequency is known as threshold frequency. Got it?
Yes.
Or it should have certain minimum energy. I can talk about the frequency, or if the frequency is not given, I can talk about the energy. The photon should have minimum energy. What that energy of the minimum energy required to remove electron, that is known as work function. Okay, so the energy of the photon should be at least equal to work function or more than that. Then only the electron is going to get released. Otherwise, if the photons are of less energy, the electrons will not be removed. Is it clear?
Yes, sir.
So this is the photon. This is what is happening, right? The frequency of the photon should be greater than the threshold frequency, or the energy of the photon should be greater than equal to the work function. This work function is represented by psi naught. This is a Greek. This is just a symbol. Work function is the minimum amount of energy which is required to remove the electron from the surface of a metal. Is it clear or no?
Yes, sir.
Right? So this is photoelectric effect, and that actually tells us the particle nature of light. Okay. So suppose if you imagine that light to be wave nature, so wave is continuously coming, right? So what you can imagine that if I keep on putting light of lower energy, because wave is continuous, at some point the energy will accumulate and will remove the electron. Okay, but that doesn't happen. If you take a low energy light whose energy is less than work function or whose frequency is less than the threshold frequency, no matter how long you irradiate on the metal, the electrons will not be released. Is it clear? So this experiment can
Yes.
be explained by by assuming that it is a light is a stream of particle, and those stream of particles are continuously coming and hitting the metal surface one by one. Electrons are being ejected, but that hit should be of the proper energy. Okay, it is like, suppose if I try to push my table for 1 hour with a very less amount of force with just one finger, my table will not move whether I push it for 1 day or 2 days. Okay, if I'm not putting appropriate force, will it move? No. Getting my point
No.
of view? So same way,
Yes.
the electron is going to come out. Photoelectric emission or the photocurrent will be visible only if you put the photon of minimum energy. For that minimum energy is known as work function, or the frequency, minimum frequency, that is known as threshold frequency. Got it? Is that clear?
Yes.
So
Yes,
we
sir.
will continue it on the next class, and then we can move on to the line spectrum of an atom. That will take us to the Bohr model. Okay. So let me end today's
Okay.
class. Right. Okay. Bye bye. Take care.